Welcome students. Let us continue our properties of conductors in electrostatic equilibrium right from the previous video. So we are going to study about the properties. So we are studying about the properties of conductors in electrostatic equilibrium. So let us consider these properties of conductors in electrostatic equilibrium here, and here we are going to consider about the second property. So what is the property number 2, or what is the second concept? See, there is no net charge inside the conductor. The second property is there is no net charge. There is no net charge inside the conductor. There is no net charge inside what? Inside the conductor. That is, the charges must reside only on the surface, of the conductor. So what do you mean by this, or how you can able to explain this? See, in order to explain this, let us consider a metallic conductor. See, we are going to consider a metallic conductor of any shape. Okay, let us consider a metallic conductor. See, we are going to prove this concept. That is, there is no net charge. That is, charge is Q, which is equal to 0 inside the conductor. We are going to prove this. Okay, let us write like this. We are going to prove with Gauss law. We are going to prove this with the Gauss law. How we are going to prove this? So since we are going to prove this with the Gauss law, what I am going to consider is, I am considering a Gaussian surface. See, inside or near the surface of the conductor, I am considering a closed surface, a closed imaginary surface, and this closed imaginary surface, I am calling this as what I am taking, and I am taking this as Gaussian surface. See, when you are considering a Gaussian surface, the flux available in the Gaussian surface is given by phi is equal to closed integral of E vector dot dA vector, or I can write Q divided by Q enclosed divided by epsilon naught. This we have already studied in our previous videos with the help of the Gauss law. See, when I am considering this Gaussian surface, the Gaussian surface is very close to the surface of the conductor. See, I am considering the Gaussian surface very close to the surface of the conductor. Okay. Why we are considering it as very close to the surface of the conductor? Because inside the Gaussian surface, you are going to prove the charge inside is equal to 0. So the maximum amount of area is considered. Now, we know that the flux available is equal to closed integral of E into dA vector, which is equal to Q enclosed by epsilon 0. As we know from property 1, see the previous property that we have studied from the property 1, the first property or the property 1, that electrical field E is equal to 0 inside the conductor. Isn't it? We have proved inside the conductor electrical field is equal to 0. See, if so, flux is also equal to 0. Isn't it? You apply it in that equation. See, when you are applying it in this equation, you will be very clearly say that phi is equal to, see, phi is equal to closed integral of E vector dot dA vector, which is equal to, here this E vector inside this Gaussian surface is 0 because it is inside the conductor. So flux available is equal to 0, which is equal to Q enclosed divided by epsilon 0. Therefore, I can write phi is equal to 0, which is equal to the charge enclosed Q by epsilon 0. Therefore, by making a cross multiplication, you can very well say that the charge inside this conductor is equal to what? The charge inside this conductor is equal to 0. See, after finishing all the remaining two properties, let us summarize. Now, let us move on to the third property. What is the third property? Let us consider the third property. The electrical field outside the conductor is, see, the third property is the electric field outside the conductor, when you are applying an external electrical field externally. See, when an electrical field or the electrical field outside the conductor is always or is perpendicular to the surface of the conductor, to the surface of the conductor, and this is what one point, and along with this we are having one more point, and it has a magnitude. That electrical field has a magnitude. It has a magnitude equal to magnitude of the electrical field. It has a magnitude of sigma divided by epsilon 0, where the sigma is the surface charge density. How you can explain this and how you can prove this may be asked for a 3-mark problem. See, the property is the electrical field outside the conductor is perpendicular to the surface of the conductor, and it has a magnitude of sigma by epsilon 0, where sigma is the surface charge density. See, in order to explain this, let us consider a conductor. See, let us consider a spherical conductor, or let us take a part of a spherical conductor. Okay, in that spherical conductor, I have considered a part. See, in order to explain it as it is in your book, what I am doing, I am considering an external electrical field. When I am considering external electrical field, the external electrical field, we know always it is represented by drawing parallel lines. Isn't it? External electrical field, if it is uniform, then it is represented by drawing parallel lines. Okay, I am considering parallel lines which is expressing or which is representing an uniform electric field, and let us consider this uniform electrical field as E. This uniform electrical field which is applied externally on reaching the surface, it will be perpendicular to that of the surface. The angle between these two is 90 degrees. Similarly, when it is coming, it will be slightly inclined so that the angle between them is 90. If you are drawing here, it will be coming like this. In order to get the angle between them as 90. If you are drawing this like this, and after this it will bend around in order to make the angle is considered to be 90. See, if you are taking the external electrical lines of force produced by the external electrical field, when it meets the surface, always the angle between the surface and the electrical lines of force or electrical field lines is considered to be perpendicular to each other. This is the concept given. The electrical field outside the conductor is always perpendicular. In order to explain this, let us take in a contrary manner. What we are going to consider? If you are taking that, if the electrical field lines are not perpendicular to the surface, what will happen? Let us consider like that. See, let us take like this. If the electrical field lines, if the electrical field lines are not perpendicular, then it will have a parallel component. Then it will have a parallel component. Isn't it? If it is not perpendicular means then it will have then it is considered to be parallel. So if it is a parallel component, what will happen? The electrons will experience acceleration. Isn't it? If you are having the parallel component, the movement of the electron and the electrical field lines, if they are parallel, then the electrons will experience a force or the electrons will get accelerated. So, if the electrical field lines are not perpendicular, then it will have a parallel component. So, the electrons inside the conductor, when you are considering the electrons inside the conductor will experience a force or experience an acceleration. If the electrons are said to get accelerated, then the conductor is not in electrostatic equilibrium. If so, the conductor is not in electrostatic equilibrium. Then the conductor is not in electrostatic equilibrium because the electrons will move in a particular direction. But we proved that, or we know that the conductors are in, but we know that the conductors are in electrostatic equilibrium. So, what is the conclusion? Therefore, we can say that, the electrical field lines are perpendicular to that of the surface. Therefore, it is proved that the electric field is perpendicular to the surface. Okay, this is considered to be the second concept. See, while you are stating this property, we are considering about two concepts. One of the concept is the electrical field outside the conductor is perpendicular. That we have proved. Now, the electrical field has a magnitude of sigma by epsilon 0. How you can able to prove it out? See, how you can able to prove it out means, we have to consider a Gaussian surface and with the help of Gauss law, let us prove it out. So, in order to prove the second part, that is, to prove the magnitude of the electrical field equal to, okay, the next concept, to prove the magnitude of the electrical field E equal to sigma by epsilon 0. How I can able to prove this? So, in order to prove this, what I am going to consider is, I am taking an closed surface, okay. I am considering a conductor of this shape. Okay. If you are considering a conductor of this shape, in this conductor, you consider an Gaussian surface in the form of a cylinder embedded inside the conductor. Okay. So part of the Gaussian surface is outside and another part of the Gaussian surface is inside. So it is piercing inside the conductor, and here another part of the conductor is a cylindrical conductor. Another part of the Gaussian surface is said to be available outside. This conductor is having the charge which is distributed. Okay. So the charge is available inside the conductor. I am taking it as positive. See, if you are having a positive charge inside this conductor, then we can say the electrical field will be acting. Then I can say the electrical field will be acting radially outwards or perpendicular to that of what? Perpendicular to that of the surface. If you are dropping a normal, that normal is also along the same line, n cap. Now, what I am going to do now? In order to prove that the electrical field outside the conductor is equal to sigma by epsilon 0, apply Gauss law. So, I am writing it like this, applying Gauss law. How you can apply Gauss law? We know that closed integral of E vector dot dA vector is equal to closed integral of E into dA into cos theta equal to the total charge enclosed divided by epsilon 0. Now, what is the value of closed integral of E dA cos theta? How I can write this for the Gaussian surface that I have considered? The Gaussian surface that I have considered is having a curved surface, then top closed surface or top end cap, and the bottom end cap inside the conductor. So I can write this equation as closed integral of E into dA into cos theta equal to integral over the curved surface where E into dA into cos. See, when you are considering this curved surface, the angle available is normal drawn will be in this direction. Electrical field will be in this direction. So angle theta equal to 90 degree in the curved surface. So E into dA into cos 90 plus integral of E into dA into cos of, where I have to calculate the top end or the top surface where the direction of the electrical field and dA vector or n cap, dA vector or n cap, both are along the same line. So in this position for the top end theta equal to 0, so it is cos 0. Again plus inside this metal conductor you will be having what? Inside this metal conductor you will be having the bottom end. So integral of the bottom end or the bottom surface, you can say E into dA into cos 0. See here cos 90 becomes 0, so the whole term becomes 0. In this case, the electrical field E inside the conductor is 0, so the whole term becomes 0 since E equal to 0. So the only term available is E into dA into cos 0. Therefore, I can write flux is equal to So let us consider the flux value. Therefore, the flux phi is equal to integral over the top surface E into dA, which is equal to, E is considered to be constant. What is this dA? When you are integrating, you are able to get it out as A, which is equal to, according to Gauss law, it is Q by epsilon 0. Let us consider this equation. Now you see, what is this Q? But here Q is considered to be the charge enclosed inside the Gaussian surface. Charge enclosed inside the Gaussian surface is how I can able to calculate for the given Gaussian surface. Surface charge density sigma equal to Q by A. Therefore, the total charge Q equal to sigma into A. Therefore, substituting in this equation, one can write as EA is equal to Q, instead of Q, sigma A by epsilon 0. So here A will get cancelled. Therefore, I can state, how I can state, therefore electrical field is equal to sigma divided by epsilon 0. So we have proved. So we can write hence proved. This is considered to be the third property. What is the fourth and the final property? So let us consider the fourth and the final property like this. What is the fourth property? In the fourth property, we are going to talk about the potential. So point number 4, the property number 4. What is the fourth property? The electrostatic potential. Okay, we are going to study about or state about the potential. The electrostatic potential. The electrostatic potential has the same value. Has the same value on the surface and inside the conductor and inside of the conductor. Inside the conductor is more correct. Okay. How you can able to say this? What is the property? The electrostatic potential has the same value on the surface of the conductor as well as inside the conductor. Both inside and on the surface, they are having the same value. See, how I can able to explain this? Already we have stated that. See, already we have studied that. We have studied that the electrical field has no parallel component. The electrical field has no parallel component, isn't it? If parallel component is available, then it will disturb the electrostatic equilibrium of the conductors. So only perpendicular component is available. So we have already studied that the electrical field has no parallel component, or we can say no parallel component on the surface of what? No parallel component on the surface. Okay, let us write like this. No parallel component on the surface. See, if there is no parallel component on the surface, for example, we have taken a conductor. On the surface of the conductor, there is no parallel component. If there is no parallel component, means there is no force or there is no acceleration. So I am considering a charge on the surface. If I am considering a charge on the surface, since there is no parallel component, no work is required in order to move the charge from the point A to the point B. So the charge can be moved from one point to another point. Then no work is said to be done. What do you mean by this? Already you have studied in equipotential surface. No work is said to be done on the surface of an surface if the potentials are same. See, the potential at this point and the potential at this point are same. So no work is said to be done, or no external work is being done in order to move that charge. Then the surface is considered to be an equipotential surface. That's all. So what do you mean by this? This means, this means that a charge placed on the surface, a charge placed on the surface can move from one point to another. Can move from one point to another. Then no work is done on the charge. No work is done on the charge. See, there is no work is done on the charge means we can say that is the potentials on the surface are same. That is, the potentials on the surface at all points are same. At all points are same. Or we can say, how we can say, that means the surface is the surface is an equipotential surface. That is, the surface is an equipotential surface. One point. So external, when you are considering on the surface, the potentials are considered to be same everywhere. The surface itself is acting like what? The surface itself is acting like an equipotential surface. That was the meaning. Since what happens to inside? See, when you are considering inside, when a point is considered inside, or when potential is considered inside, potential is considered inside, it is same as that of the surface, same as that of the surface. Why? It is same as that of the surface since electrical field E inside the conductor is equal to 0. Since the electrical field inside the conductor is equal to 0, we can say that the potential on the surface is same as that of what? As that of inside. Thus, at electrostatic equilibrium, thus we can say at electrostatic equilibrium, the conductor is always, or the surface of the conductor is always, the surface of the conductor is always equipotential. Equipotential. It is not necessary that we have to say it is surface, because both the surface as well as inside the conductor is having the same potential. So we can say that the conductor is considered to have the same potential everywhere when the conductor is said to be in electrostatic equilibrium. These 3 points, or these 3 are called to be the properties of what? Properties of the properties of conductors in electrostatic equilibrium. All the 4 properties, including the concept of conductors in electrostatic equilibrium, may be asked for what? May be asked for an 5-mark question. Hope you should have understood. Okay, then the next concept we will say in the next video.